Perfect. Okay, so welcome today to the ACPMS seminar, and I'm happy to have Ruggero Bandiera as a speaker, and he will talk about cumulants, Koszul brackets, and homological perturbation theory for commutative B infinity and IBL infinity algebras. Please.
Okay, thank you very much for inviting me to speak. Okay, so as the title suggests, I want to talk mostly about homotopy transfer via homological perturbation theory. And let me start. Oh, this is not. Let's do it like this. Okay, and let me start by reviewing some standard material about L-infinity algebra first. So let's begin by setting out some notations. So we denote by SV, given a graded space V, we denote by SV the symmetric coalgebra over V with this coproduct where we denote by, use this notation for the I n minus I unshuffles. And as you all know, this is the free coalgebra in an appropriate sense. And in particular, as in a free algebra, a derivation is completely determined by its restriction to the generators. In a free coalgebra, dually we have that a co-derivation is completely described by its co-restriction. So we have isomorphism of graded space, which basically means that to give a co-derivation is the same as to give a bunch of maps, its co-restriction. So we restrict it to V to the n and then project onto V. And conversely, we can reconstruct Q from these maps, which we call the Taylor coefficients, explicitly via the following formula. And then we can define an L-infinity algebra, actually an L-infinity one, we call it algebra, essentially as a DG coalgebra whose underlying coalgebra is co-free, so as a co-derivation on SV, which squares to 0 and with trivial constant part. And so again, to check this relation, it is enough to check that the co-restriction of Q squared vanishes. And this translates into a bunch of identities on the Taylor coefficients Qn. And the relation with L-infinity, with Lie algebra is establishing first by switching degrees. So this will turn this degree 1 maps on V into degree Q minus n maps on V shifted. And this also introduces a sign which turns these graded symmetric maps into graded antisymmetric maps. And in terms of these new maps, these graded antisymmetric higher brackets, the required relation become the following one. So the unary bracket should define a differential, and this should satisfy the Leibniz relation with respect to the quadratic bracket. And then the latter should satisfy the Jacobi identity up to a homotopy, which is explicitly given by the tertiary bracket, and so on. So we get that the brackets inarity from 2 to n will satisfy a higher Jacobi relation up to a homotopy, which is given by n+1 bracket. So in this sense, L-infinity algebras can be seen as generalizations up to homotopy of DG Lie algebras. And in particular, a de Gilli algebra can be seen as L-infinity algebra with only the first two brackets non-trivial. Okay, we can similarly define L-infinity morphism once we have two L-infinity algebras. An L-infinity morphism is just a morphism between the corresponding DG coalgebras. And so, since these are free coalgebras, these are completely determined once again by their co-restriction. So by these maps, which we call the Taylor coefficients. And again, we can explicitly reconstruct f from its Taylor coefficients. And here is the explicit formulas to do so. Okay. So L-infinity algebra provides a context where one can do homotopy theory. And the resulting homotopy category is equivalent to that of de Gilli algebra. So they provide an equivalent model for de Gilli algebras up to quasi-isomorphism. But they have additional flexibility in all the coherent homotopies that they carry. And to illustrate this additional flexibility, let me introduce the main subject of the talk, this homotopy transfer theorem. Basically, for de Gilli algebras, if we have two quasi-isomorphic complexes and de Gilli algebra structure on one of them, there is no meaningful way to transfer this to a quasi-isomorphic de Gilli algebra structure on the other one. But we can transfer it to an L-infinity algebra structure. This is the point. And in fact, if we have more structure than just quasi-isomorphism, if we have contraction between complexes, then we can do so very explicitly. So let me recall you what I mean by a contraction of complexes. These are quasi-inverses, quasi-isomorphism, satisfying some extra side condition, which are this one and the last line. And in this situation, so when we have a contraction of the complex V onto W, and then we have an L-infinity algebra structure on V, we can transfer it explicitly to an L-infinity algebra structure on W. And moreover, there are induced L-infinity quasi-isomorphism in both directions, both from W to V and from V to W. And as I said, we can do it very explicitly, and in particular for the Taylor coefficients of the morphism F and of the L-infinity algebra structure on W, we have the following well-known recursive formulas. And so let me just point out right now that by their nature, these formula are well adapted to inductive arguments. So suppose we want to prove that these coefficients F and R satisfy some extra properties. And we know the Q satisfies, so the L-infinity algebra structure that we are transferring satisfying corresponding properties, then this formula leads naturally to inductive arguments. And these are well known, and a little bit less known, we can be explicit also about the other morphism G, the one going from V to W. So to do so, we starting from the contraction of V onto W, we can construct a contraction of the symmetric powers of V onto the symmetric powers of W. And this is the explicit formula for the contracting homotopy. Now, we starting with this contracting homotopy, the coefficients of G can be computed explicitly by the following recursion. So we first apply this contracting homotopy, then we apply the Q and project onto the I components, and then we apply GI. Okay. And in the first part of the talk, the plan is to sketch a proof of this theorem that I just told you. And the proof follows a well-known and well-established idea. So first you apply the symmetrized tensor trick and then homological perturbation theory. So let's start with the first step. So here we have the differential Q1 and R1 on V and W respectively. This extends to linear coderivation, in fact B derivations on SV and SW. And then the previous Hn sigma, the one that we write down explicitly before, this example to a contracting homotopy of this for the symmetric powers of V. So in turn, we have an induced contraction from the symmetric coalgebra over V with the linear coderivation extending Q1 onto the symmetric coalgebra over W with the collinear coderivation extending R1. And this is known as the tensor trick. Since we are doing it in the context of symmetric coalgebra, this is known as the symmetrized tensor trick. And then the second piece of data is the following well-known lemma, known as the homological perturbation lemma. So here we start with a contraction, and we suppose that we have a perturbation of the differential on the bigger complex A. And by perturbation, I mean a map which, when added to the differential, squares to 0. Then, if these infinite sums converge, and this hypothesis will be automatically satisfied in all the cases we want to apply this theorem, this lemma, then this formula defines a perturbation on this delta B will be a perturbation of the differential on B. And this formula defines a perturbed contraction of the perturbed A onto the perturbed B. So now the idea is we start with the symmetrized tensor trick, and we regard the L-infinity algebra structure on V as a perturbation of the differential on SV. Because it's square to 0 by hypothesis, so we can apply to this situation the previous lemma, and we have a perturbed contraction. These infinite sums will be automatically convergent. Now the problem will be to show that this perturbed contraction does the trick, or so we want to prove that this perturbed R is a coderivation. We already know that it squares to 0 by the homological perturbation lemma. And we have to prove that these are coalgebra morphisms. We already know that they are compatible with the differentials. So this is really not this idea is really not new, and in fact is 50 years old, but in the context of A infinity algebras. This is the usual way to prove this theorem, working with A infinity algebras rather than AL, so associative algebras up to homotopy. These are defined much in the same way as L infinity algebras, but using the tensor coalgebras rather than the symmetric coalgebras. And there you can define the tensor trick much in the same way as before, but we can avoid this sum here, this symmetrization step. So we can define the homotopy in this case in a simpler way. And the point is that this simpler homotopy will satisfy strong compatibilities with the coproduct. It will be what is known as a coderivation homotopy. The problem is that when we symmetrize, we lose this property. So the usual proof for A infinity algebra doesn't carry over automatically to L infinity algebras, because we don't have a coderivation homotopy anymore. So the first thing that we want to explain that this is not a coderivation homotopy, but it still satisfies enough compatibility with the coproduct that are enough to do the trick, essentially. So we want to explain what kind of compatibility it satisfies with the coproduct. And so let me start with a contraction of complexes. And let me do first the algebra case. So assume we have algebra structures on A and B. We don't suppose this differential to be derivations. We say that the contraction is a semi-full algebra contraction if satisfy the following identities with respect to the product. So notice these identities again don't involve the differential here, so only involves the products on A and B. And we can give a dual definition for coalgebras. So if we have coalgebra structures this time on A and B, we say that the contraction is a semi-full coalgebra contraction if it satisfies this dual set of identities. And as an example of a contraction which satisfies this kind of compatibilities, well, the point is that the contraction in the symmetrized tensor trick is not a coderivation homotopy, nor a derivation homotopy, but it satisfies this condition with respect both to the natural product and the natural coproducts on these spaces. So we might call it a semi-full bialgebra contraction. It satisfies all these conditions with respect to the natural products and coproducts. Okay, now assuming this fact, what can we do with this fact? The nice thing about this, I'm sorry, I'm going now. The nice thing about these formulas is that they are stable under perturbation. So we have the following key lemma. If we start with a semi-full coalgebra contraction or algebra contraction, and we apply an arbitrary perturbation, again, we are not assuming any kind of compatibility between this perturbation and the product or coproduct. So for any perturbation, the perturbed contraction will continue to be a semi-full algebra or coalgebra contraction. And this is really very easy to see if you try, because for instance, you start with this identity, you want to prove that this is 0, and you use the perturbation formulas for H, and you expand this thing, and you see that all the terms in the expansion will contain this term here, which is 0 by hypothesis. So it will be automatic that the perturbed homotopy will continue to satisfy this condition. And similarly for the other cases, if you try, it is very easy to see that these formulas are stable under perturbation. And so now this is useful, very useful. We can combine these two pieces of information with the previous argument. So here we apply the tensor, we apply the homological perturbation lemma. We know that we started with a semi-full bialgebra contraction. The conclusion is this perturbed contraction will still be a semi-full bialgebra contraction. So appropriately compatible with both the product and the coproduct. And now we are almost done. We combine this with, so this is what I just said. And now we combine this fact with a last lemma that says that if we further assume in a semi-full algebra contraction that the differential on A is a derivation, then the same conclusion for B is automatic, and moreover, it is automatic that F has to be an algebra morphism. And now for the application to the homotopy transfer theorem, we are really interested in the dual statement. So if we start with a semi-full coalgebra, if we have a semi-full coalgebra contraction like this one, FGH, and if the differential is a coderivation like Q is, then it is automatic that R is also a coderivation. So it is an L-infinity algebra structure, and G, this G here, is a coalgebra morphism, so it's an L-infinity morphism. And the proof is so simple, actually, surprisingly simple, that I can't resist showing it to you. So you start with this, and first you use the fact that you have a contraction, so this thing between parentheses is just the identity. Then you split the sum. In the last term, you use the hypothesis that the A is a coderivation to move it to the left of the coproduct, and then G is a morphism of complexes, so you move it to the left again. And now this thing here is 0 by the semi-full coalgebra condition. And so is this. So these two terms go away. And this thing here is just the coproduct of B, again, by the semi-full coalgebra condition. I'm using this one and this one. And so what remains is this. We are done already. And the proof for the other statement is similarly very easy. Here we use G, that we use again the identity related to the coproduct on A and B. In the here, then we use that G is a morphism of complexes to move this to the left. Then we use the dA is a coderivation to move it to the right, sorry. Then F is a morphism of complexes, and then again the previous identity, and we are done. So it's very, very easy. But this proof doesn't seem to be well known, I mean. And we are almost, with this very simple argument, we are almost finished. The only thing that remains to be proven is this statement that F is a morphism of coalgebra. And let me point out that this is a bit surprising because usually, I mean, this is well established. This morphism is well known. G is the more esoteric one, the one that you want to find in most formulation of the homotopy transfer theorem. So to the best of my knowledge, BVoo was the first one to give a full statement for both directions. So. But with this approach, the fact that G is in an L-infinity morphism actually is very easy. And F, the better known one, is the one that requires a little bit more work. So now if we were only interested in completing the proof, we could give maybe some more direct argument. But instead, let me make a digression which will be useful going further. And so let me put away for a moment the discussion about the homotopy transfer theorem and let me introduce two related constructions. The first construction I want to discuss is the one of the cumulant, as known as cumulants. So the context is this. We have two graded commutative algebras A and B and a map between these algebras. And to this map, we can associate graded symmetric maps, which we call its cumulants, which measure the deviation of F from being an algebra morphism. These first few formulas illustrate. And in general, we have this formula where we make this summation run over the unordered partitions. So essentially, this is a hierarchy of maps which measure in a coherent way this deviation of F from being an algebra morphism. And similarly, the Koszul brackets are maps which we can associate to an endomorphism of a graded commutative algebra A, which measure in a coherent way the deviation of this map from B an algebra derivation. And in this case, this is illustrated by these first few cases. And here is the general formula. Now, but both constructions are classical, I mean, and were introduced independently from each other in different contexts. And what is interesting, and maybe not known or not well known, at least, is that they admit unified. There is a unified approach to define both these constructions. So the idea is this: we start with a graded commutative algebra A, and then SA is the free algebra generated by A, and in particular, we have a natural algebra map from SA to A, which extend the identity. And now the idea is to regard this algebra map as the co-restriction of an automorphism of the coalgebra SA. So again, to define a morphism of coalgebra is enough to define its Taylor coefficients, and these Taylor coefficients are the one in this map, so are defined simply by the product of the elements. And this defines an automorphism of this coalgebra, whose inverse can be computed explicitly. It is easy, and it will be the morphism with Taylor coefficients given by this formula. And we will call this the exponential automorphism and this the logarithmic automorphism, because this is essentially what these are doing at the level of the diagonal. They are taking the exponential and the logarithm. And now we can use these maps to prove the following proposition. So we can relate on the one hand the linear differential, the linear coderivation extending D, and on the other hand the coderivation with Taylor coefficients, the Koszul brackets of D. And the claim is that these are the latter is the conjugate of the former by the exponential automorphism. And this can be proved directly by a simple computation. If you try, it's not hard to see it directly. And there is a similar description for the cumulants. You can prove directly with a simple computation that these are the conjugate of the morphism which extend F linearly using the exponential of A and the logarithm on B. And now, if you have this way to construct the Koszul brackets on the one hand and the cumulants on the other hand, several properties of this construction that are not immediately apparent from the explicit definitions here and here and here. Well, with this proposition, it becomes very easy to prove stuff like the cumulants are compatible with composition. The Koszul brackets are compatible with the commutator bracket on the one side and the commutator of endomorphism on the other side. These are all well-known properties, but this will give an immediate proof of these properties. Here in the last identity, what I'm saying is assuming that dA is a differential, so it squares to 0. Then by this fact, we know that the corresponding coderivation square to 0, so is an L-infinity algebra structure on A, shifted, which is well known. So this is an L-infinity 1 algebra structure, and similarly, this is an L-infinity 1 algebra structure on B. And this formula shows that the cumulants of F, if this is true, so if F is a morphism of complexes, its cumulants will define an L-infinity morphism between the corresponding L-infinity algebras. Another fact that is, so another easy consequence of this proposition is that the cumulants are an exponential version of the Koszul brackets in the following sense. Here we start with endomorphism D. So KD will be a coderivation of the symmetric coalgebra. Its exponential will be an automorphism of the symmetric coalgebra, because the exponential of a coderivation is a. And what I'm saying is that this is precisely the algebra morphism associated via the cumulants to the exponential of D. This, of course, provided that this exponential converges, and then so we'll do this one. Okay. And another advantage of this approach is that it makes it kind of clear what one has to do to adapt the definition in the dual coalgebra case. So how to define cocumulants and Koszul co-brackets. So again, we start with a coalgebra, commutative, and we want it to be locally conilpotent. What it means locally conilpotence, and the iterated coproduct vanish on C. The higher enough iterated coproduct will vanish when evaluated on a given C. So this infinite sum become finite when we evaluate it on some elements of C, and it defines the unique coalgebra morphism extending the identity of C, since this is the Kofri coalgebra. So we start with the unique coalgebra morphism extending the identity of C. And this time we see it as the restriction of an algebra automorphism of SC, this time seen as the symmetric algebra over C. So an algebra automorphism is determined by its restriction to the generator, and this is what we take. Again, we get an automorphism whose inverse is given by this logarithmic formula. And we can use these automorphisms to conjugate respectively morphism of coderivation to get the desired definition. So if we have a map from C to C, its Koszul brackets will be defined as the components of the derivation, which is the conjugate of the linear derivation extending D by this co-exponential automorphism. And similarly, we can do for the Koszul brackets. So we can define the Koszul brackets of a map as the components of this conjugation of the natural algebra morphism induced by F. And again, with this definition, this map will measure in a coherent way the deviation of D and F from B respectively coderivation or a coalgebra morphism. Okay. And now another useful lemma, this time a more technical one, but it is useful for several of the results that I want to illustrate in the final part of the talk. So we start with a semi-full algebra contraction of A onto B. And again, we are not assuming that this is a derivation of the algebra structure. So its Koszul brackets KDA will define an L-infinity algebra structure on A. A non-trivial one. If this was a derivation, only the first one will be non-trivial. So if we have a contraction, we can transfer this L-infinity algebra structure as we explained. So we get an L-infinity algebra structure on B and morphism in both ways. And the lemma states that the transferred structure on B will be the one associated to the Koszul brackets. And the transferred morphism the canonical one, let's say, the one going from the smaller algebra to the bigger one, will be associated to the cumulants of this F. And let me briefly explain why this can complete the proof of the homotopy transfer theorem. So the point is that we can combine this lemma with two other results which might be of independent interest because at first sight they are kind of unexpected. So suppose we have this morphism between SW and SV, and we want to understand if it is a coalgebra morphism. Well, we know that this is equivalent to the cocumulants of F should vanish, the higher cocumulants of F should vanish. But the maybe surprising fact is that we can also give a condition for F to be a coalgebra morphism, which instead only involves the cumulants of F. which is unexpected because this map a priori should measure the deviation of F from being an algebra morphism rather than a coalgebra. But we can use this map to give this condition for F to be coalgebra morphism. The condition is that we want the Koszul bracket of F to send the symmetric powers of W, seen inside here, inside V. So there should be maps Fn mapped in this diagram commutative. This will be not automatic for a generic F. And when we have these maps, one can see that F is precisely the coalgebra morphism with these maps as Taylor coefficients. And one can give a similar characterization of coderivation in terms of Koszul brackets. So similarly, we can take the Koszul, we can start with a map Q, and this is a coderivation if and only if its Koszul brackets restricted to symmetric powers of V take values into V. This will be not automatic. But when this happens, so we have maps Qn making this diagram commutative, then Q is a coderivation and it's precisely the coderivation with these Taylor coefficients. So how can we combine these two results to complete the homotopy transfer? The point is that the only thing we are remain to prove is that F is a coalgebra morphism. And this proposition gives a condition to verify this in terms of the Koszul brackets of F. But we know that FGH is a semi-full coalgebra contraction, so the Koszul brackets of F are induced via homotopy transfer. So the cumulants of F, I'm sorry, are induced via homotopy transfer from the Koszul brackets of Q, which is a coderivation. So now we can apply the second proposition and an inductive argument to see that F satisfies the required property. Recall the recursive nature of the formulas in the homotopy transfer theorem. This allows to do the desired induction. Okay. So this completes the argument, but let me see a bit more things that we can do with what we said so far. So now let me introduce commutative BV infinity algebra in the sense of Kravchenko. So first, let me recall you this well-known fact, which states that the Koszul brackets emit recursive definitions where the n+1 bracket measure the deviation of the n1 from being a multiderivation, which is what this formula is saying. And then in particular, if one bracket vanish, all the brackets after that will vanish as well. And when this happens, D is said to be a differential operator of order minor or equal to n if all the brackets major than n vanish. And this will recover the algebraic definition of differential operator by Grothendieck. And so I needed this to recall this definition by Olga Kravchenko. So we start with a commutative algebra and a bunch of maps from A to A, which are these delta I. And we assemble into a unique Katie-linear map from the formal power series on A into itself. And we say that this is a BV infinity operator if it satisfies three conditions. We want it to square to 0. if A has an identity, we want a unity, we want it to vanish on the unit. Finally, the most interesting one is that this should satisfy appropriate compatibilities with the product, and more precisely, we want this delta n to be a differential operator of order less or equal than n-1, and this for all n. So the first one will be a derivation, the second one will be a differential operator of order less or equal than 2, and so on. And in particular, this recovers the usual definition of BV algebra when all the operator after the first two vanish. A convenient way for us to reformulate this last condition, the third one, is in terms of Koszul brackets. So we say that for this to be a differential operator of this order means that all the brackets after this one will vanish. So all these brackets will vanish when ENN satisfy this relation, and this can be compactly formulated in this way. So we want the n Koszul bracket of the total operator to vanish modulo t alla n minus 1, and this for all n greater or equal than 2. The reason why this formulation is convenient is that, I mean, this definition provides a homotopy version of BV algebra, where we are relaxing up to homotopy the condition that the BV operator squares to 0. On the other hand, this is not a full homotopy BV algebra in the operatic sense, because we are maintaining strict commutativity of the algebra and strict compatibility between the operators and the algebra structure. So we are relaxing up to homotopy, but only in one direction. So in this situation, it is not clear how to define infinity morphism between these objects. The usual operatic machinery doesn't apply directly. But this last condition and the previous analysis suggests such a definition. So when we have a commutative algebra with a BV infinity operator in the previous sense, we call it a commutative BV infinity algebra. And we can define morphisms between these objects by mimicking the previous definition. So we will want a morphism of complexes preserving the units, and the last condition can be adapted by substituting the Koszul brackets with the cumulants. And this is a justification of this fact is that by the previous relation that we established between cumulants and Koszul brackets, it can be shown that this condition is precisely the exponential of this one. So if you take a degree of 0 operator that satisfies this condition, this exponential will satisfy this one, and conversely. So with this definition of morphism, BV infinity algebras form a category. And another advantage of this point of view is it makes it clear how to define dually BV infinity coalgebras and BV infinity and morphisms between these objects, because given a coalgebra, a B infinity operator will be an operator squaring to 0, satisfying an analog condition with respect to the co-unit, And then the latter condition can be reformulated in terms of Koszul brackets. We want the Koszul brackets, the nth one, to vanish modulo Tn minus 1 for all n. And similarly for the morphism. Okay. Now, the following slides was to mention a relation between BV infinity algebra in this sense and L infinity algebras. But since we are a bit short on time, let me be a bit quick. So the point is that to a BV infinity algebra in this sense, we can associate an L infinity algebra, essentially by taking the first non-trivial component of this map, of these Koszul brackets. And since by the previous identity here, this one, since the successive Koszul bracket has to vanish, this says that this is a multiderivation in all of his arguments. And moreover, it is easy to see that this will be the coefficients of an L infinity algebra. So we have an L infinity algebra where all Taylor coefficients are multiderivation. This is a generalization of homotopy of Poisson algebras, where again we are relaxing up to homotopy only one direction, the one of the Jacob identity, and not the full picture. And this will give a form functor from BV infinity algebras to BV infinity algebras in this sense. Okay. So finally, let me come to the homotopy transfer theorem for BV infinity algebras. This is not hard. So suppose we have two DG algebras and a semi-full algebra contraction between these. And then we have a BV infinity operator on the bigger algebra extending the differential. So in this situation, how can we try to transfer this operator to the smaller algebra? Well, first of all, we can extend the contraction by KT linearity. And so we get a contraction from formal power series on A to formal power series with coefficients in B. And now the BV infinity algebra structure can be seen as a perturbation of the differential on this algebra. So we can apply the perturbation lemma. And again, this will give a perturbed differential on BT and a perturbed contraction of AT on 2BT. In this situation, it's really very easy to write down explicit formulas. Here they are. I mean, it's quite immediate. And the point is that in this hypothesis, here the key hypothesis is that this contraction is a semi-full algebra contraction. So this is a semi-strong hypothesis. This theorem has a limited range of application because of this necessary hypothesis. But in this situation, this naive way to do homotopy transfer works, and this transferred operator on B will be a BV infinity operator. And moreover, we can also say that this perturbed F will be a BV infinity morphism. While for the other one, I don't have a conclusive statement at the moment. It seems a bit more complicated. It is also interesting that, so this is proved by the previous key lemma. We want to prove that these transfer operators, the Koszul brackets of this transfer operator satisfy certain conditions. Since the contraction is semi-full, we can relate the Koszul brackets of this operator and the Koszul bracket of this operator. So we can apply the homotopy transfer formula and induction to get the desired conclusion. Anyway, a case when we can apply this theorem, and this luckily an interesting enough case, is when the underlying algebra or coalgebras are free or co-free, and we start with the contraction induced by the symmetrized tensor trick. But we can do so because we already know that this will satisfy the necessary condition. It is a semi-full bialgebra contraction. And the reason this is interesting is because these objects, so BV infinity algebras or coalgebras from underlying algebra is free or co-free, are known to model certain kind of bialgebras up to homotopy, and namely involutively bialgebras up to coherent homotopies. And this structure were introduced by Chelibak, Foucault, and Latchev, and several applications in all these fields that you see written here, neither of which I'm an expert on. In any case, for bialgebra type objects, homotopy transfer becomes more complicated. And it is interesting that for these objects, we can do it in the usual naive way. So we get an homotopy transfer theorem for this type of object. So for the purposes of this talk, the more convenient definition will be that IBL infinity algebra is a BV infinity coalgebra structure on SV. I mean, this is kind of dual of the more usual one where you could say that it's a BV infinity algebra structure, but since involutive bialgebras are self-dual, a self-dual notion, this will get the same thing in the end. In any case, we start with such an object, and then the BV infinity operator, its first term will be a coderivation. So it will be an L infinity algebra structure in the usual sense. And in particular, it will have a differential, a unary bracket. And so this defines the differential the complex structure on V. And suppose we have a quasi-isomorphic complex W. In fact, suppose we have a contraction. Then we can transfer the full IBL infinity algebra structure on V to a corresponding structure on W. And moreover, we get IBL infinity morphism, that is morphism of BV infinity coalgebras in both directions. And the idea is to do the usual one. We applied symmetrized tensor trick and then homological perturbation theories in this IBL infinity algebra structure as a perturbation of the linear differential extending this. And it's convenient, I'm almost done. It is convenient to break the proof into two steps. In the first step, I mean, we already said that this IBL infinity algebra structure on V in particular contains delta zero, which is an L infinity algebra structure. So we can apply usual homotopy transfer theorem as we explained it at the beginning of the talk. So we get a transfer L infinity algebra structure on W and a perturbed contraction. And now we have, we can see the full IBL infinity algebra structure as a BV infinity coalgebra. So we have the previous homotopy transfer theorem for BV infinity coalgebras that applies in this situation because this contraction is semi-full. And so by the homotopy transfer theorem, this almost completes the proof because this already says that this is a BV infinity operator, so an IBL infinity algebra structure. and already says that one of the two morphisms, the one going, this one G, the one going from V to W. This we already know from the homotopy transfer theorem for BV infinity coalgebras to be an IBL infinity morphism. So as in the L infinity case, the only thing that remains to be proven is the corresponding statement for F. And this is solved in a similar way as we did for in the L infinity algebra case. So for this to be an IBL infinity morphism, this is a condition in terms of its co-cumulants. But we can give an equivalent condition in terms of its cumulants. And here it is. We want that its cumulants restricted to VW, restricted to symmetric powers of W factor to the inclusion of a certain subspace, which is this subspace here. So the moral is, again, we can equivalently, so the condition that this is a BV infinity coalgebra morphism can be equivalently stated in terms of cumulants when we can apply the key technical lemma and recursive arguments to prove that these two conditions in this proposition will be satisfied. And that is all. I mean, thank you, but I'll go back to the previous slide. So.
Thank you very much. Thank you. Other questions or remarks or comments? Maybe I start with a question regarding your definition of cumulants as a sort of thing to measure the failure of being an algebra morphism. So you start from commutative or non-commutative algebras, A and B?
No. Everything is in the commutative words. I mean, in the non-commutative world, you can follow a similar approach, but here you want to replace in the discussion everywhere the symmetric algebra with the tensor one. So you will start with the natural morphisms from the tensor algebra. You extend to a coalgebra automorphism, and then you use this to conjugate. And for cumulants, you will get a non-commutative analogous of the cumulants by very simple formulas. And for the Koszul bracket, you get a non-commutative analog of this that was introduced by Borgeson. These are known as the I hope I'm probably pronouncing it. These are known as the Borgeson brackets.
So but these, sorry, I didn't want to
sorry.
interrupt.
What's
then if you sort of express, if you use these cumulants, I guess somewhere, maybe you stated this, I would imagine some formula that involves summation over partitions or something like this. But if you go from commutative to non-commutative, would you still expect sort of a sort of moment cumulant formula that should express this sort of failure of an algebra morphism to be in terms of regular set partitions or something slightly different?
Honestly, I'm not sure, but what I can give you is a reference here. I mean, this definition that I gave you of BV infinity algebra morphism is I'm sorry.
Sorry.
Okay. How do I remove this? Yeah. So this paper here. This construction were used by Park in the context of what he calls non-commutative probability theory. So I'm not sure there was But here he uses
yes,
the
this was my.
commutative case actually. So
Yeah.
the,
I mean, I
I'm
think
sorry, the answer is I'm not
he's
sure.
he's a co-author of the paper. I wanted to ask you whether there's a link to the work of Drummond, Cole, Terila, and Park about this, what they call homotopy probability, where they start, I think, if I'm not mistaken, essentially from the same problem, sort of using cumulants to understand the failure of a map being an algebra morphism. But somehow they arrive at, I think, in this very simple case, at Boolean cumulants.
Well, I can tell you there. So these non-commutative cumulants that you get with this approach will be given by formulas similar as this one. Here you sum over the
Yes.
compositions of n. So n equal I1 plus up to ik. You give an order partition of n. And then you sum over this order partition. You don't have this Koszul sign because the arguments remain in order, and you don't
Yes.
have this factorial, but you have the same sign. So you have this
I see.
alternating sum over the composition of n of the product. So this is the kind of maps that you get with this approach in the associative case.
Okay. Okay.
So I'm not sure the relation to classical probability because there I'm a little ignorant on the subject, and I'm afraid.
Okay. Okay. Are there other maybe questions or comments or remarks? Okay. Maybe so this is not the case. Okay, then good. Okay, then thank you again for this
Of
talk.
course, thank you for
Okay,
inviting.
and then let me tell you. So the next talk will take place on the 5th of April. This is because I think in 2 weeks, the 29th of March, it's a holiday, I believe. And so we will continue then with a talk by William Turner, which will be, I think, in the direction of rough paths and free probability. And so, okay, I wish you a nice weekend, and then hope to see you in
Thank you
early
to you
April.
too.